Hello everyone and welcome back to this channel. In today's video, we are going to solve this problem using the conservation of mechanical energy. Let's look at the problem. A grasshopper launches itself at an angle of 45 degrees above the horizontal and rises to a maximum height of 1.00 meters during the leap. Now, with what speed did it leave the ground? And in this problem, we are neglecting air resistance. Alright, let's look at the solution. At first sight, you may think this is a projectile motion problem. Of course, it is, but going the projectile motion approach is going to be time consuming, and it is going to be a very difficult problem to solve using the projectile motion approach. As such, I will show you how to use the conservation of energy to solve this problem in a few steps. Now we have to draw a free body diagram. In drawing our free body diagram, we need a coordinate system. In this case, we are going to use the XY coordinate system, also known as the Cartesian coordinate system. So having my coordinate system here with my x-axis here and the y-axis here. So the x-axis specifies the horizontal motion and then the vertical axis specifies the vertical motion. Whilst I place my origin here, since it launches from the origin, we can place the grasshopper at this point, which is our origin, and it launched itself at an angle of 45 degrees to the horizontal. Now, it is the speed or the initial velocity vector that makes this angle with the horizontal axis. In that case, the initial velocity vector is going to point this direction. Let's call that VI, alright? And that makes an angle of theta, which we know the angle to be 45 degrees to the horizontal. Now, the trajectory of this grasshopper is going to be a parabola such that it reaches a maximum height as seen here, as given in the problem. So at the maximum height, this bag is going to be at this point, and that the height at that point is h equals 1.00 meters. So that is given. Now the goal is to determine the initial launch speed with which this bag took off until it got to this 1 meter height. Alright, now with this initial speed, since it makes an angle of theta with the horizontal, we need to resolve it to get the initial horizontal velocity and as well as the vertical initial velocity. So in doing so, we need to generate a right triangle. So this side here becomes the opposite side. So that would be our VIY, that is the initial speed in the vertical direction. And then this side here, that is the adjacent side, is going to be VIX, that is the initial speed in the horizontal direction. Now applying trigonometry, we can find out that cosine gives us that VIX is going to be equal to VI, which is the hypotenuse, and then cosine of the angle theta. In the same sense, VIY is going to be VI sine of the angle theta. Alright, so we need these two equations to solve this problem. However, we are going to see the physics later, as in how these two are important at that point here to solve that problem. Alright, with projectile motion, we know that at the maximum height, that is when h equals 1 meter, now the only speed would be the horizontal speed, because acceleration of free fall does not affect the horizontal speed, it only affects the vertical speed. So at that height, the horizontal speed, which is Vx, would be the same as VIX, whilst our Vy is just 0 at the maximum height. Alright, so that is the physics at this point, because at the maximum height, the vertical velocity becomes 0 because the bag should momentarily stop and then return back, completing the other half of the parabola. However, because there's no effect of gravitational pull on the horizontal speed, it remains constant. So let's look at the data we know from this problem. So data, we know that the angle it makes is 45 degrees. Also, we know that that height is 1.00 meters. We are given g, or g would be 9.8 meters per second squared, and then the Vx at the maximum height is going to be our Vix. In that case, it would be Vi cosine of theta. Alright, so with this we can solve the problem. Alright, so using the conservation of mechanical energy, we know that the initial total energy of of this bag when it is at this point should be equal to the final total energy when the bag is at the height of 1 meters. So let's look at that. So initially there's going to be two energies. We have the potential energy, gravitational, plus the kinetic energy, initial. So all for the initial case, that is at the starting point where it launched itself with the initial speed of vi. That should be equal to, at this point where it is 1 meter high, from the 0 point vertically, the potential energy gravitation plus the kinetic energy final at that point. So in the conservation of energy problems, all you need to do is to consider 2 points along this trajectory. So if we know the initial information at the start of the motion, the total energy at that point should be equal to the total energy at some other point we are interested in that case at h equals 1.00 meters. Now, what is potential energy? It is the energy possessed by this bag by virtue of its position, and that energy is given by m, g, and h. All right, so wherever we see potential energy, we are going to substitute this value or this equation in there, and then the kinetic energy, ke, is given as 1/2 the mass of the bag times the velocity of the bag at that point square. All right, so this is the equation for the kinetic energy, and kinetic energy is nothing but the energy possessed by a moving object. All right, so in this case the bag is moving, it will have some kinetic energy. If it has some position or some height with respect to the origin, then it is going to have some potential energy. Good, now let's plug these two equations into the initial and the final cases, simplify it, and then solve the problem. So in that case, the potential energy becomes mgh initial plus 1/2 mv squared initial. All right, so that's the initial total energy initial. That should be equal to mgh final. That's the final height. That's the height of 1 meter that we are interested in at that point, plus the kinetic energy at that point. So as I stated earlier, it would have no vertical speed, however possesses kinetic energy because it has the horizontal speed, which the horizontal speed we know remains constant throughout the motion because acceleration of free fall does not act on the horizontal speed. So that gives us 1/2 mv final squared. V final indicating at that final point we are interested in. All right, now we can see that the m or the mass is common, so that cancels out. And then we can see a fraction. Some of those terms are multiplied by 1/2, so we have to remove these fractions. So what we do is to multiply each term by 2. So here by 2, here by 2, here by 2, and then multiply this last term by 2. Now this 2 cancels that, so it goes out, right? This 2 also cancels that, so that goes out, and then we are left with a simplified equation, which now is 2ghi plus vi squared equals 2ghf plus vf squared. All right, now the hi, the initial height, is 0, so that clearly indicates that it started from the origin, so no height, so that term also goes to 0. Okay? And then we have further simplified the problem or the equation to vi squared equals 2ghf plus vf squared. But this vf, in this case, that is the vx at the maximum height. That is the vx at 1.00 meters high. So that vf now becomes our vi cosine of 45 degrees because the theta is 45. Now we can substitute that into the equation, and then we are going to have a much nicer equation, which is vi squared equals 2g. Now hf is our h, which we know, plus vi cosine of 45 also all squared. All right, now the cosine of 45 is square root of 2 divided by 2. Okay, so substituting that in there would give us vi squared equals 1/2 of vi squared over 2. That is evaluating the cosine of 45, which is square root of 2 on 2 squared, will give us 1/2. So 1/2 times this vi squared would give us vi squared over 2, and then plus 2gh. All right, simplifying this for our vi, we are going to see that vi is equal to 2 square root of gh. All right, substituting our value will give us 2 square root of 9.8, and that is about 6.2 meters per second as the speed with which this grasshopper launched itself. And that is very interesting. Even though we see such bugs as very weak, look at the speed with which it's launched itself from the ground. 6.2 meters per second, and that is a very powerful grasshopper. All right, so this is the end of this problem. As usual, let's promote this channel by liking, sharing, and subscribing to the channel if this is our first time. If not, let's just keep sharing and doing physics. Until then, I'll see you in my next video. Thank you.